Hello, my name is Advik Prabhu, and today we're going to learn about expected value. This is the seventh and last episode in the Counting and Probability or Combinatorics course. So, in this video, we'll cover over expected value and what weird paradoxes occur with expected value, as well as doing a review once this all ends. What is an expected value? Well, first, let's get to know what an average is. An average, which is the sum of all the um, numbers in a data set. So if you have like 1, 2, 3, 4, 5, the average denoted as this of this set is equal to the first element is equal to the first element plus the second element plus the third element plus the fourth element plus the fifth element divided by all the elements. And if you compute this out, it would be 15 over 5 or 3. So 3 is the average. And expected value is what we would expect to get if we, instead of like our average number in this data set, what if we had a dice? Well, what would we expect to get? And that's kind of a weird, overly confusing definition. So instead, let's get an example. Let's say we flipped a coin, and if it gets heads, we get $2, and tails, we lose $1. Now, kind of intuitively, you think that you're gonna you think that you're expected to gain money, and so you'd play this game. But how much would you be expected to win? Well, let's say we did this coin flip about 1,000 times, and we would expect to get 500 heads and 500 tails. 500 heads would gain us $1,000, and 500 tails would lose us $500. So after that 1,000 flips, we're expected to get about $500. And dividing that by 1,000, you would get about 50 cents or half a dollar every time you flip a coin. But that's like kind of confusing. Like, why this is so much steps? So and it's not really a formal definition. We kind of just said if you would expect to get this. Like, how would you know that? Especially if the probability isn't 50-50. Well, a formal definition is for any event where all the probabilities of all the possibilities add up to 1, the expected value is the product of each probability and the associated value. Now, let's go back to our earlier example. Let's say we flip a coin and heads, we get $2, and tails, we lose 1. Well, by our definition, does the sum of the probabilities add up to 1? Well, there's a 1/2 chance of this and a 1/2 chance of that. 1/2 plus 1/2 is 1. So this expected value is just the probability into the value plus the probability into the value. And that's our expected value. Wait, it's a capital E. So what is the probability? 1/2 into 2 plus 1/2 into -1, or 1 minus 0.5. Or you're expected to get 1/2 of a dollar, or 50 cents. So, yeah. So now we kind of understand how he works, and we tested it on a simple example. So let's quickly speed through some problems just to get like understanding of it. So here's 3 problems. I'm gonna go over very fast, so try to solve it on your own, and then I'll get to it. Okay, so in our coin flipping example, so if you get heads, hails, we win $3. And if you get tails, we lose $2. Well, there's a 1/2 chance of heads and a 1/2 chance of tails. So you'd get 1/2 or which is equal to 1.5 minus 1, or you still expect to get 50 cents. Okay, now let's go on to our second problem. If every outcome of some event has a positive value, does that imply that the expected value is positive? Why or why not? Well, if the probability of, so we got P of 1, P of 2, all the way to P of n. And we got, X of 1, X of 2, all the way to X of n. Okay? So we know that all of these values are greater than 0, because probabilities are greater than 0, especially if we know it's going to happen. It's less than 1, but that doesn't really matter. And we know all of these are greater than 0, because they're positive. So that means the product of P of 1 into X of 1 is always greater than 0. So when we add a bunch of values that we know are positive, we will get a positive number. So, yes, if every outcome of some event has a positive value, that means the expected value is positive. Just logically, that makes sense. If we're always expected to gain money whenever we play something, then is it possible to lose money or not get any money if you play the game? Okay, finally our last one. If an event has only two outcomes with values 1 and 0, and the probability of the outcome with 1 occurring is P, then what is the expected value? Well, think of this as you got P of 0, P of 1, X of 0, X of 1. So our expected value is just P of 0, X of 0, plus P of 1, X of 1. I should have started with 1 and went to 2, but yeah. And this, plug in our values of P, 1 minus P, because that's the complement, 0 and 1, you get 1 minus P, 1 minus P into 0, plus 1 into P, which is equal to 1 into P, because multiplying with 0 doesn't do anything, which is equal to P. So the probability that the value 1 occurs is P, and the expected value is P. Okay, next problem. Suppose we have a weighted coin in which heads come up with probability 3/4 and tails with probability 1/4. If you flip heads, you win $2, and if you flip tails, you lose 1. What is the expected value of the coin flip? So let's go through this really quick. We have 3/4 chance of heads, heads, yeah, and that in that case you win $1. And you have a 1/4 chance of tails, in which you lose $1. Multiplying this all out, you get 1.5 minus 1/4, or 0.25. Therefore, you're expected to win about $1.25, or $1.25 every single time you flip a coin. One of the main uses of expected value is to figure out what's a fair price to play something. So if you had this at a cardinal game, you're expected to gain about $1.25. So you should probably charge $1.30 or $1.50. In that case, you're going to make a profit. But if you charge $1, then you're going to expect to lose about 25 cents each time you play. So now this is kind of uncommon to occur mathematically, but in real life this can come up. Let's say someone gives you a bag with 12 slips of paper in it. Some of the slips have a 2 and the rest have a 7. And you just do experimental probability, you just keep drawing and you guess that the expected value is about 3.25. Then how many slips have a 2? So let's say X slips have a 2. So X slips have a 2. And you take X over 12, because that's the probability of picking a 2, times 2, plus 12 minus X, because that's a complement. And you're saying that number is equal to 3.25. If you simplify the left side, you get 84 minus 5x over 12 is equal to 3.25. And if you solve this, you get x is equal to 9, which means there's 9 2's and there's 3 7's. So let's say you have a 6-sided dice, such as the probability is weighted that the probability of any number being rolled is proportional to the value of the roll. So P of 6 is equal to 6 times P of 1. So just quickly, if you calculate the probability of every single thing, we get 6 times probability of 1 plus 5 times the probability of 1 plus 4 times the probability of 1 plus 3 times the probability of 1 plus 2 times the probability of 1 plus the probability of 1 is equal to 1. If you find this, 11, 15, 18, 20, 21, 21 times the value of probability of 1 is equal to 1. So the probability of getting a 1 is 1 over 21. The probability of getting a 2 is 2 over 21. The probability of getting 3 is a 3 over 21. The probability of getting a 4 is a 4 over 21. So on and so forth. And multiplying and adding all of this out results in, so if you do this, you can simplify this to 1 squared plus 2 squared plus 3 squared plus 4 squared all the way to 6 squared over 21, which is equal to 13 over 3. So you're expected to get about a 4 every time you roll it. So now let's go to like weird funkiness that occurs with expected value. Let's say you're playing a game in which the prize pool starts at $1. On every turn, you flip a fair coin. If you flip heads, then the prize pool doubles. If you flip tails, the game ends and you win the prize pool. What's the expected value of your winnings? So we might think about calculating the probability. So like, how many outcomes are there? Well, you can get tails, you can get heads and then tails, you can get heads, and then tails, so on and so forth. And you might realize that there's infinitely many outcomes. So let's just make a table, okay, in which we write how many heads occur. Well, 0 heads if our first thing is tails, then we get $1, and this occurs with probability. Let's create a three-way table, or like this. Okay, the outcome, the probability, and then the winning. So if we get none, there's no heads that occur, which happens with the probability of 1/2, and you win $1. You can get 1 heads, 2 heads, 3 heads, and let's just say go on and so forth. 1/4, 1/8, oh sorry, 2, 1/8, 4, 1/16, 8. Okay, and let's just calculate the expected value of like just the first few ones. Multiplying these two, you get 1/2. 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 And you realize you're just adding infinite 1/2s. So your expectation's infinite. But how can you get infinite money? Well, the thing is, you can't play this in real life. Cause what happens if like the person gets really lucky and flips like a incredibly high number of heads? Well, then in that case, if they flip that much heads, you don't have enough money. So in real life, this game would have to end eventually, which means expected value would have to be finite. So another funky game, this one's a lot easier to calculate. I offer you 2 envelopes, and I tell that one has twice as much money as the other one. I don't tell you which envelope is which though. You choose an envelope, open it, and then you point to keep the money at the envelope, or switch and keep the money in the other envelope. You choose one envelope at random, open it, and find $10. What is the expected value of your winnings if you switch to the other envelope? Well, either the other envelope has $5 or $20 in it, and there's 1/2 probability of each. So you're expected to get more if you flip, because if you multiply these out, you get 12.5. So if the envelope you have has $10, and the envelope that you switch to has expectation of $12.50. So yes, you should switch envelopes. But does like $10 actually mean anything? Does it matter how much money you find in the first envelope? Well, let's see. Let's say A is the number of money you see. Well, there's a 1/2 chance of having half of A. And there's a 1/2 chance of having 2 times A. So A plus A over 4. That's how much you're expected to gain if you switch. So no, it does not matter, because this is always going to be greater than the actual money itself. Well, since each envelope has a 50-50 chance of being the higher amount, there should be clearly no value of switching. Or, to put it another way, the strategy of switching should be as good as just keeping the same thing. But our answer shows that no, that's not really true. And this looks like a paradox. But it's kind of hard to resolve this. So it requires a lot more complicated probability techniques. So I'll leave you to think about this for now. So now let's go over a review. These problems are harder, but but I will be going over them pretty fast. So yeah. So I'm just gonna tell you the strategy, and kind of you get this through like logic more than anything else. So basically, the strategy is to stop drawing white balls if you draw a white ball first, and if a black ball is drawn first, continue drawing until both white balls are removed. So if you'll examine the expected outcome of this strategy, um, there is 10 different possibilities of drawing balls. But the main ones are the following. The main thing is the following. There is a 50% chance that you win $1, which occurs if you pick up your white ball first, or you pick up a black ball first, and then pick up 2 white balls right after. You have a 1/5 chance of not getting any money, and that occurs if you pick up a black ball as your first one, and then pick up one more black ball before picking up both white balls. Sorry, not this, 1/5. And finally, there's a 3/10 chance that you lose $1, which occurs if you draw every single ball before. Yeah. So this is an expected value of 0.5 plus 0 minus 3/10, which is 0.3. So you're expected to get about 20 cents. And that results in a profit. Now this one's a cool problem. If you have a treasure worth $100,000 and it landed in a swamp, and if you don't find it within a day, it'll sink in the bottom and you lost it. And you can hire as much helicopters as you want. So how many helicopters should you hire? Well, this is kind of hard to solve mathematically, so let's just do trial and error. So if it's one helicopter, there's a 90% chance of recovering your treasure. So 0.9 times 100,000. Okay, so you get like a 90,000 thing. But you spent $1,000, so you actually get an $89,000 expected profit. If you buy two, well, then you got a 99% chance of finding it, so you're expected to get 99000. But you spent 2,000, so your expected thing is 97000. Finally, if you buy three, your expected, then the cost of the helicopters is at least $300,000, and whatever amount of money you get is about this much, cause $3,000. And this isn't even with a certainty. It's like some value that's less than 1 times 100,000 times it's like 0.999 less than 1. But the cost of $3,000 already makes it less not as good as this one. So the best number of ones you should buy is 2. So this is a pretty hard problem. Let's say Caitlin and Olivia are playing a game. Caitlin starts with 1,000 pennies, $10, I think. Yeah, $10. And Olivia starts $5. On each turn, one of them flips a quarter. If the quarter comes up heads, Caitlin gives Olivia a penny. If the quarter comes up tails, Olivia gives Caitlin a penny. The game ends when one of them runs out of penny. It's a pretty long game. What is the probability that Caitlin wins? So, this one's kind of hard to solve mathematically. So let's just say the probability that Caitlin wins is P, and see if there's something we can do to be able to like solve this. So let the probability that Caitlin wins be P. Eventually one of them has to win, so Olivia is 1 minus P. If Caitlin wins, she ends up with 1,500 coins, and if she loses, she ends up with 0 coins. Okay, so the expected value is equal to the probability that she wins times 1,500 coins that you'll get, plus the probability that she loses times 0, because that's how much coins you'll end up, which is 1,500 times the probability of her winning. Since on every term Caitlin has an equal chance of gaining or losing a penny, the expected value could actually just be the 1,000 she already has, which means that you got this equation. And dividing both sides by 1,500, you get the probability of her winning is 2/3. This is a very good example of expected value, because what we did was find the expected value of the number of coins in terms of the probability of her winning, and then find out what that expected value was through logic, and then use that to calculate the probability. Overall, what we did is like overall, what we did is we went over what expected value was and the formal definition of it, and some paradoxes you can get, as well as some problems that help stress how important they are. Expected value is very useful in a lot of cases, and in real life too. Like if you're playing a game that requires luck, you can calculate the probability of you winning, and use that to calculate like how much should you pay for it, and whether or not the people are scamming you. So, thank you for listening. Hope you like this. Hope you like this entire like combinatorics course, and have a nice day. Bye.